All right, Calc 2 is riddled with trig. We got a whole section to where we get to do some trig and some integration. So it's pretty much your best day ever. Sweet, let's jump right in. Wait. Before we do that, here's a couple of trig identities. That should be an I, and it kind of got messed together, didn't it? Trig identities that I want to make sure that you know, remember, whatever. So Pythagorean identities first. Cosine squared plus sine squared is equal to 1. 1 plus tangent squared is equal to secant squared. Well, a lot of times you write it as cotangent squared, but frankly, it's plus 1. So tangent, any of these, it's addition, right? Is cosecant squared. So you can rework those however you want to. It's all addition. All right, so there's some Pythag identities. Also, those half angle identities that we've talked about already, I call them power reducing, but those are going to be super handy whenever you integrate. So sine squared is 1/2 1 minus cosine 2x, and cosine squared is the exact same thing except plus. All right, it's those double angles. All right, okay, now let's dive in. If I have something like this, scoot this up a little bit. So that's all just trig review, so that's what we already have. Here's example 1. I would like to integrate cosine to the 5th x dx. All right. Anytime you have an odd sine or cosine. Now, let me preface it by saying, remember in 8.1 we said, oh, a lot of the concepts here, we're going to move forward. And then we were doing those trig problems and I said, sit tight, we're going to do a whole section on them. Welcome to that section. All right, that's what's happening right now. For this problem, here are some keys. Oh, let's do something other than red because we used that earlier. Odd sine or cosine, odd degree of sine or cosine, pull one out for the u sub. We're going to do a lot of u sub. All right, that's why we need to know the Pythagorean identities, and that's why we need to work with this, because we're going to do a lot of u sub is what's going to be happening here. Okay? So for this one, if I work with this, I have cosine to the 4th x, and then I have cosine x dx. All right? Well, I keep going back and forth. I'm probably making y'all sick. Sorry about that. But check this out. This is an even exponent, right? You now have an even exponent. So go to your toolbox. What do we know? We know our identities, where that becomes even. We also know over here that the derivative of cosine here is going to be negative sine. The derivative of sine is cosine, right? Okay, when you do a u sub, you're looking at derivatives, right? All right. Over here, I know that the derivative of sine is cosine. We already know that. If you don't know it, learn it, because that's important. Here, I can convert, because this is to an even power, I can manipulate my Pythagorean identity here, and I can say, all right, 1 minus sine squared x is equal to cosine squared x. That's just a manipulation. And then we can replace that. Check it out. So now I end up with here as 1 minus sine squared x to the 4th lies, that's squared, because this is the same thing as cosine squared takes out a square, power to a power, you multiply, right? Okay. So here we've got that, and then I've got cosine x dx. Now we do our u sub. I'm going to scoot it up just a little bit. u is equal to the sine of x, and du is equal to the cosine x dx. I like to think about working these almost backwards, where I want to pull out my du. I want to figure out, what is that du? What is that odd exponent? And I'm going to pull that out to be my du. If I can focus on that part of it, everything else has to be in terms of sine. It has to be in terms of that u, because now I just have a polynomial. Okay, 1 minus u squared du. Polynomial, yo. So yes, these are trig integrals. However, we're going to do a u sub and put this in terms of polynomials, and then we can just do our basic polynomials, right? All right, so multiply that out. It's squared, so 1 minus 2u squared plus u to the 4th du, right? Square the first term. Multiply those together by 2. Square the last term. And then integrate. So u minus, and when you add that, would be 2/3 u cubed. Add 1 to that is a 1/5 u to the 5th. It's indefinite. Now I put sine in there everywhere, and we go with it. Sine of x minus 2/3 sine cubed x plus a 1/5 sine to the 5th x plus c. All right. You start off with cosine to the 5th. I can't integrate that exactly like it is, because there's no such thing as a chain rule with integration, right? I have to break it down in terms of plus or minus, so it's things that I can actually integrate. So we use our identities to pull that off. When I solve these problems, I like to look for, what is my odd exponent? If you have an odd exponent, pull that out and you can work with it. All right? Okay. What if I just have an even exponent? Example 1b. I am integrating sine to the 4th x dx. Right? That is when we use power reducing. Power reducing. If I don't have an odd exponent to pull out, I'm going to make this smaller so you know it's an exponent. If I don't have an odd exponent to pull out, then we use our power reducing. Remember, sine squared, I can reduce that to be a 1/2 1 minus cosine 2x. So I'm going to write this step here. This is sine squared x squared. Last time we just did it in our head on that last example, but this is what you're actually doing, right? So I'm going to take this and plug it in. There's no u sub at this point because it's an even exponent. Odd exponents go for u sub with sine and cosine, just with sine and cosine. Okay, so now I'm integrating this 1/2 1 minus cosine 2x, and this whole thing is squared. Right? Now I've got that 1/2 squared. I'm going to chuck that in front. So I've got a 1/4, because it's just a number. We can put that in front. Then I've got 1 minus cosine 2x squared. So FOIL that out. Square the first term minus 2 times the second term. And then square the last term. Right? Can I do something that's squared? No. So what do we get to do? Another power reducing. Good job, you guys. So I know that cosine squared is going to be 1/2 1 plus cosine 2x. Now I want to point something out to you right here. My inside function is a 2x. So when I plug that in for x, I'm going to do 2 times that 2x, because this goes in for the x. Do you see that? I'm just going to keep rewriting this because we'll just integrate all at once. Plus a 1/2 times 1 plus cosine of 4x. Because this is 2 times the 2x, because the 2x is that inside function. All right? okay, clean it up a little bit. Look what happens. If you distribute this 1/2 to both terms, you'll get this 1/2 right here that you can put with a 1. And then it's that 1/2 cosine 4x. I'm going to scoot it up again. So the 1/4 goes in front. And I have 1 plus 1/2 is going to be 3/2, because that's 1 1/2, right? Minus 2 cosines of 2x plus 1/2 cosine of 4x dx. Now, ladies and gentlemen, we can integrate. All right? Because I just have that inside value. So I've got 1/4. Here I have 3/2 x minus, when you take the antiderivative of cosine, right? So your antiderivative of cosine is going to be sine. So this is sine 2x, but I've got this 2 in front, and because I've got this inside function here of 2, remember that's a divided by 2 situation. So that's really a 1. Okay. Plus, and I have this 1/2 in front. Again, I've got sine of 4x, but I'm going to bring that 1/4 in front here. See that? Plus c. All right. Now, I'm just going to distribute this 1/4 and clean it up. I don't know what I was doing that. So I've got 3/8 x minus 1/4 sine of 2x plus, what's 8 times 4? 32. And that is our final answer. Did we ever do a U sub in this whole problem? No, but did we use the dickens out of those identities? Yes, we did. Yes, we did. So here's the moral of this story. With sine and cosine, if you have an odd exponent, pull it out for a U sub. If you have only even exponents, then you have to do those power reducing. Sometimes you get to do it more than once, but you get to do a bunch of power reducing. All right? Okay.